now we're going to turn attention to the DSEM model. So this is again the model that we're working on now. So this is the residual DSEM model, and so the model is defined slightly differently. So the within level model, the within level variables. So here the dependent and the latent variables on the within level model, they actually further split into two separate levels, which I called here the level 0 and the hat level. And the hat basically refers to the residual, and this would refer to the structural part, all the predictors. So we split it to show you what our DSEM model is. We basically have this additional, so the within level level is actually split into two separate levels. This level will contain the structural part of the variables, and this will be the autoregressive part of the variables. And we basically wanted to separate, there was a lot of interest in separating the predicting part of the equation from the autoregressive part of the equation. And so the equation now on the within level looks like that. So this, the level 0 part contains all these the prediction portion of the equation, and the autoregressive part of the equation is now separated. So basically all the hat variables here, they are regressed on each other, but they do not contain any of these prediction variables. And so basically the covariates are excluded from the autoregressive part of the equation. We will talk more about this in the examples. To specify completely this DSEM model, we also have to specify the initial conditions. So when we talk about these regression equations here, when you start the sequence, say at time t equals 1, you're going to get these variables that have negative indices and 0 indices. So you have to start somewhere. And there's different ways to do this, different approaches in the literature. But what we do in Mplus, we actually treat these parameters, these variables basically, that are with negative indices, we treat these as auxiliary parameters. They have their own prior. In general, these initial conditions, they're called initial conditions, they don't affect much of the model estimation as long as the time series is 50 points or more. Even with 20 points, probably the effect of this initial condition is very small. And basically the prior does not affect the results. However, for some small time series situations, these priors can have some minor effects. In Mplus, there are two options that are implemented, and the first option is the default option. It's something we do. We actually provide these priors for you, so you don't have to worry about them. So they're automatic priors, and we have this in the MCMC estimation. We have during the first 100 burn-in iterations, we update these priors of the initial conditions. What we do, so we start at standard normal priors for the initial conditions, and we keep iterating through the MCMC sequence, and at each iteration we update this prior to the sample quantities for each of the variables. So for example, to get the prior for eta with negative indices, after the first iterations those etas are imputed, and we compute the sample mean and the sample variance, and we set that to be the prior for the etas with the negative indices. And after the burn-in iterations, those burn-in iterations are discarded. They're not part of the iterations that we use to estimate the estimates of the model. So those are discarded, and that's necessary to make sure that the MCMC sequence that we use for the estimation is properly defined. So that's a very standard way of dealing with such issues. And this approach seems to be working quite well. And so we basically, I was working on this maybe more than a year ago, and pretty much nobody actually uses now anything but that at this point. it seems to work quite well in practice and even in simulation studies as well. The second approach, which is available to you and you can use it, is you can actually specify your own priors for these initial conditions in the model prior statement. So the model prior statement generally is used to actually specify the priors for the model parameters, but now you can actually have, with DSEM models, you can also use actual variables from the model. So f is a factor here, you can use the variable from the model and specify a prior, and same thing for the dependent variable y here. And what that means, the interpretation of this is that you're specifying the priors for the initial conditions. But again, this is fairly tricky to use, especially when your variables are not standardized, and it's not even very straightforward to figure out what the proper mean should be in these situations. So generally, we don't recommend that we recommend that you use our default approach. So there's some features that are not available. We just kind of had to put an endpoint to actually release the program at some point. So those are not available, but they might be available in future versions. So non-recursive models are not available. That's actually generally for our base estimation. We don't have these models. This actually came up twice yesterday. So this is basically the lag zero regression coefficients between dependent variables. Those cannot be random at this point. Random loadings, currently they can be subject specific, but they cannot be time specific. They cannot have a time specific component. And we also don't have for categorical variables. The underlying y star, the lagged version of the underlying y star variable, that cannot be in the model. So the only way to actually do time series models with categorical variables is when they are used as measurement for a factor that has time series model. And that might actually be also resolved in the next one of the next versions of Mplus. So the DSEM estimation is, again, it's a Bayesian estimation. It's an MCMC estimation with a Gibbs sampler. We basically, the way the estimation works is we determine all the unknown quantities in the model. These are basically all latent variable, missing values, initial conditions, random effects, and the model parameters. And we split all these unknown quantities in the model into blocks. And we basically, in the Mplus estimation, these are the 13 blocks that we split the unknown quantities in, and those are basically the MCMC iteration basically updates each of these blocks using the conditional distribution that for each block we determine the conditional distribution of that block conditional on all other blocks, and as we iterate through the blocks, we basically update the quantity for each unknown value here. And we construct these distributions. As we keep iterating, we monitor the posterior distribution for each unknown quantity. Actually, we just monitor the model parameters. And as the sequence progresses, it stabilizes, the distribution stabilizes, and we conclude that the sequence converges, and then we use this the distribution that is being generated from the MCMC sequence to construct point estimate, standard errors, and so on. So the reason we actually use these 13 blocks, so that we have our strategy for actually estimating this is to we use some sort of a mini-max strategy. So we want to have the smallest amount of blocks that would allow us to have explicit posterior conditional distributions, so that we can easily generate values from the conditional distributions. We want these blocks to be as large as possible, as to provide good mixing. So if there are quantities and non-quantities in the model that are highly correlated, those have to be grouped in the same blocks. Otherwise, we'll create this slow mixing that would actually make the sequence, the convergence of the sequence, very slow. So we basically want to have the smallest amount of blocks, but what that causes is, of course, that these are very large. These blocks become very large, and so the conditional distributions are very complex, more complex than if you just update one quantity at a time. But nevertheless, we want to have these big blocks to actually get a fast convergence. Once each block is determined, we actually split every block into sub-blocks. There are, we find the smallest sub-blocks of elements that are independent, conditionally independent. So we actually generate from the smallest conditionally independent sub-blocks. So this is basically our strategy for the DSEM estimation and in general for our Bayes estimation. So there's some things. So for example, if you know how we estimate two-level models in Mplus, so here's the individual level intercept, and also these are the slopes. In two-level, we actually, this is one block in two-level models. Now, in DSEM models, they're actually separated because of these centering issues, and the fact is that in DSEM models, this is not conditionally normal. The joint distribution of these two is not conditionally normal, so that's why they're separated. So it looks a little more complicated than the standard two-level model estimation. And there is another complexity, a little complication here. There's certain blocks in this set, so these are block 3, 6, and 7, that the posterior distribution is not, is actually, the conditional distribution is very large. So the conditional distribution of this term, which is basically the time-specific contribution conditional on all other blocks, it turns out that the size of that conditional distribution is the size of t. And we've made this algorithm to work with any size t, so that's not an acceptable situation. And therefore, what we have done is we actually split these blocks into time-specific blocks. And when we update these, we actually don't update the whole block as a whole, but that's actually representing these time-specific blocks. So Y3t would be updated sequentially as time increases. So, for example, at time, we first update the quantity at time equals 1, conditional on all the other times. Then we update the quantity at time equals 2, conditional on the time equals 1 and time equals 3 and so on. Then we move to point 3, update the quantity at time equals 3, conditional on the previous time points and the subsequent time points, of course, and we condition basically on the current quantities that are generated at these other known quantities. So this is kind of a little summary of what goes on. And you repeat cycling between the blocks to get this posterior distribution, and all these conditional distributions that are. So basically, the MCMC estimation consists of essentially providing these 13 conditional distributions. Once you have these 13 conditional distributions, you let the MCMC sequence generate all the unknown quantities, and you get these parameter estimates. So as long as these 13 conditional distributions are correct, you get a correct estimation.